Hello, everyone, and thanks for joining us. I'm Eric Hyam of Microwave Journal, and I'd like to welcome you to this first 2025 EDI-CON online educational day on 5G, 6G, and IoT topics. This workshop, entitled Introduction to Advanced Substrate Technologies, Thick Film, Direct Bond Copper, and Active Metal Braze for Power and RF Needs, will be given to us by Chandra Gupta of Remtec. Our platinum sponsors are Samtec and ComSol, and our track sponsors today are Mini Circuits, CPI Electron Device Business, Altair, Keysight Technologies, and Mori Microwave. Before we begin, let me cover a few logistics. If you'd like to download the presentation slides for reference, you'll find a copy in the handouts window. We'll have time for questions after the presentation. To ask one, please type it into the Q&A window at any time. The presentation is being recorded and will be available to watch again and recommend to colleagues. And with that, let me hand the session over to Chandra.
I'd like to thank Microwave Journal for allowing myself and Remtec to present Introduction to Advanced Substrate Technologies, Thick Film, Direct Bond Copper, and Active Metal Braze for microwaves and RF system engineers. A little bit about myself. I have over 35 years of experience in this industry. I'm a business development manager at Remtec, and previous to that, I was at Mini Circuits, Communications and Power Industries, Analog Devices, formerly known as Hittite Microwaves, and Aeroflex. My academic qualifications include a PhD from University of Wales and an MBA from Rutgers University. The content of my presentation will talk briefly about the need for the substrates, discuss a little bit about substrates and metallizations, multi-layer structures, key characteristics relevant to selection, products, and discussion. So design engineers have to really consider several factors in order to determine what is an optimum design or optimum substrate choice. And this involves thermal management, and that involves what is the heat dissipation as well as how it will be extracted from the substrate. Electrical properties, such as what is the power handling requirement, what is the current handling, what the voltages will be, and what will be interconnection needs. Mechanical considerations, environmental considerations such as shock, vibration, temperatures, as well as the maturity of the technology. Thick film substrates are manufactured using a screen printing process where we deposit multiple layers of conductive, resistive, and dielectric materials onto a dielectric substrate. That would be alumina, aluminum nitride, or beryllium oxide. It could be other materials as well. It is a very cost-effective, reliable, mature, and compatible technology with surface mount equipment. In terms of the thicknesses, the popular range is between 15 microns to 125 microns. The direct bond copper, DBC, consists of alumina or aluminum nitride substrate with copper films bonded to one or both sides through a high temperature oxidation process. So basically what happens, you have a copper film which is bonded to, say, alumina substrate, and it goes through, and that bonding takes place about in excess of 1000 degrees C. and that forms an oxide layer between the two. And that's how that works. They are especially well suited. This is the DBC, well suited for high power modules, automotive applications, where the heat dissipation, efficient heat dissipation is provided, and high current capacities are needed. In terms of the popular conductor thicknesses, they range from 5, 8, and 12 mil. The active metal braze involves a seed layer like titanium and then brazing of copper foils on one side or both sides to a silicon nitride substrates. It can also be done on other materials, but silicon nitride is most popular at this time. Electrical and thermal properties are very similar to DBC. These are also suited for high reliability, heat dissipation, and high current requirement applications. The popular thicknesses of the conductors range from 5 mil, 8 mil, and 12 mil. The metallization technologies, as you can see on this spectrum here, goes from low power to high power, and high density and thick film circuits in general require low power, are operating at low power, low voltages, and currents. And there we can provide high density interconnects as well as high density circuits. The next one is the what is called ENIG plating, and that involves silver or gold with electroless nickel and immersion gold. And the next one is PCTF, which stands for plated copper on thick film. And what is done here is that we start with a substrate, we put a seed layer, which could be silver, and then we electroplate the copper. And this can be typically plated up to any thickness required. The most common is up to 5 mils. At that point, DBC becomes a better choice, or sometimes would be equal choice, depending on what we are doing with it. So DBC is the next one, and that can handle more power than PCTF. And then AMB silicon nitride follows next. For those reasons, high power handling. So a little bit more about plated copper on thick film. So what it is, we start with a substrate, like the cartoon you see on the left-hand side. And what we can build, or we can drill holes into that, either laser drill or mechanically do it. We can do the plate, and these holes can be plated through holes, or they can be filled. And if you look at the layers, metallization layers, which are on the top and bottom, they can be selectively plated. So again, we'll start with a seed layer. We'll also deposit copper on it, and then we can open the windows such as that you can have copper exposed for soldering purposes. We can plate the gold in the selective areas, and one can do bonding. So this PCTF we have provided on alumina, beryllium oxide, aluminum nitride, barium titanate. These are popular materials, and you see the characteristics given there. This is ideal for surface mount work. In here, we also provide high reliability circuit, and we have via holes which are solid fill or plated through for interconnection purposes. And the via holes can also be solid filled with copper to actually provide thermal dissipation paths. So if you take a silicon or gallium arsenide and gallium nitride chips, we can provide these PTVs underneath to remove the heat from the chip. So thick film, this is another example where we start with a substrate, we metallize the surfaces, and then realize the circuit. So the metallization could be using thick film, which is screen printing, and then we can also and then it goes through the kiln or furnace, and when the surfaces are cured, then we can put dielectric layer and then repeat the metallization process again, and similarly keep doing this process to as many layers as required. Typically 6 layers are very popular. And then we can also create via holes, which are between the layers or all the way through or partial through. Blind vias, buried vias, and through vias can all be created. Metallization on the top, like is shown here, says silver, copper, nickel, gold. Is based on our customer requirements, and that can be provided for bonding purposes as well as soldering. The multi-layer, this is showing other examples of the multi-layer. So what is shown in here on the right-hand side is that we have a substrate which is in DBC. And so this particular example, we are handling high power capability as well as provide digital control and other control circuitry so that the whole circuit can be realized in a very compact package. So what you are seeing on the right-hand side, and if you look at that, the copper parts are the DBC substrate, and then the blue and the yellow substrates represent the thick film circuitry, which is a multi-layer circuitry. So those are various interconnects, and all that is provided in this multi-layer structure. And then using surface mount technology, we can actually mount chips and ICs as shown. So those what is shown on the top are the chips and the ICs. So this is a typical example one would end up doing something for IGBT circuits, which are really high power, but then the controls can be done in thick film and they don't need DBC, and then we can connect them together in a package like you see here. The example below just shows the substrates, and this is another example, which is the combination of DBC and thick film circuits. There are several product features which can be built in the DBC and AMB substrates, and this can also be extended to thick film. But what you are seeing here is plugged vias. Just like I talked about the plugged vias earlier on in the thick film PCTF example, you have the same thing here. And this shows you how the plugged via is done, and it is bore coated. As you can see, we can do step patch, which is in the middle on the top, and you can see how the different surfaces, multiplanar surfaces are created. Then we have multi-layer stack-ups, what you are seeing on the right-hand side on the top, where the circuits in each layer is slightly different, then they can be all bonded together. The bonding can be accomplished using soldering or sintering or brazing operations. Then we can also attach leads, and they can be attached, they can be brazed to the substrates like what you are seeing at the bottom left. We also provide these dimple thermal stress relief applications. So this is done, so the thing is, this part can handle multiple thermal cycles. And when I say multiple, it's like thousands of cycles. And then obviously the example at the bottom on the right is the assembly example. These are the product features developed and provided in thick film. You can see that for surface mount applications such as interconnects, etc., we can provide wraparound castellations like what you are seeing here. This is just showing you one contact. The multi-edge application can also be provided, like you can see top and bottom is traditional, but can also be done on the side. So this is the example showing you metallization on the edge. Then gold tin alloy plating, that can be done as well. And you are seeing that on the top left. The vias and this particular picture on the vias at the bottom on the left is showing you all the examples, which are showing you interconnects, buried vias, blind vias, micro vias, which are less than 5 mil. Hermeticity is achieved through making sure when the vias are there, they are filled fully, and plating is done such that nothing can go through, nothing can pass through. And then submounts and interposer applications where the boards are provided such that multiple boards can be interconnected and interface with the different interconnects of one board to the interconnect on the next board. And then the PCTF I had already covered earlier. So in the power electronics considerations, the thermal conductivity is really relevant. And what is showing here, whether we choose AMB, whether we choose DBC or examples, the choice of the substrate gives us what the thermal conductivity will be. So in terms of aluminum nitride, one can achieve about 170 watts per meter per Kelvin. So that's what the ALN is. Al2O3, which is alumina, that typically is about 30 watts per meter per Kelvin. Silicon nitride is actually halfway house between the two. So there's an error. 170 should not be at the bottom. It actually was just for ALN. So that one is about 90 watts per meter Kelvin. The other considerations which are really relevant and the designer needs to consider that the actual current carrying capacity goes up with the cross-section of the conductor, cross-section area of the conductor. So if we are looking at a PWB, or for that matter, conductor on a, say, aluminum nitride, etc., then what will happen, the cross-section area of the conductor will directly relate to the current density that can be supported. So what you are seeing in this curve here, because this is case dependent, that's why the numbers are not there. And what you are seeing that as the cross-section area increases, the current carrying capacity also increases. The skin effect is another consideration which needs to be accounted for, particularly when one goes higher up in frequency. So once we are in RF frequency, the actual currents don't flow through the bulk of the conductor. It begins to flow in the outer skin of the conductor. So what it does, whatever the DC resistance might be, it actually increases with frequency because the current is now in the skin of the conductor. So what you are seeing here, as the frequency of operation increases, the resistivity or the resistance per unit length also increases. The blue is an example of a printed circuit board example, whereas the one at the bottom is example of a coax. So depending on the case and the geometry, all that, we will get different actual numerical values, but the curves will follow the same trend, meaning basically the resistivity will go up with frequency. This shows the various products which are in the marketplace today, where you can see hermetic packages available where the actual ceramics are mounted in the actual metal packages. The other ones are ceramic packages where the interconnects are at the bottom as castellation, and there you can also have ceramic lids which can be soldered onto this package. So these are ceramic packages. Then there are examples of leadless chip carriers for RF microwave applications as well as power applications. Can also have interposers at the chip level as well as at the board levels. And these are a few of the examples you can see. Here are the RF examples. So what you're seeing on the top are a couple of substrates where for amplifier applications on the top two on the left. And then there are various examples of the filters which can be fabricated in this technology. Microelectronics it shows various examples. The first one on the left is a multi-layer board. The next one is another microelectronic circuit with the resistors printed, so the thing is ready for surface mount equipment. Then you see subsequent examples for more custom applications and custom designs to fit the form, fit, and function needs. So just to wrap it all up, we have the selection of a substrate and metallization techniques depends on what is the power handling requirement, what voltages we need to support, as well as what the current handling requirement is. Heat spreading and dissipation is also needs to be taken into account, and environmental conditions and reliability considerations have to be folded in the overall considerations. Other things to keep in mind is at DC, the current flows through the bulk of the conductor, but as one goes higher in frequency, the current flows only on the outer skin. And as it flows in the outer skin, it actually raises the resistance and also the heat generation due to that process. Thermal management, particularly over the chips and the ICs, can be provided with the use of power transfer vias, and depending on the number of power transfer vias one ends up putting, that determines the amount of heat that can be removed from the part. Just here's some information about Remtec. You can look at it on the slide, and you can find more detail about us in 2024 Fabs and Labs. Thank you, and ready for any questions and answers.
Excellent. And thank you, Chandra, for that presentation. That was a lot of great information. So we've got some questions, and let me give everyone another moment or two to add any final questions. But let's start with this one. What are the fine line and fine spacing one can get with screen printed thick film, DBC, and AMB?
Sure, great questions. The thick film using screen printing in manufacturing is typically 5 mil for the line widths, as well as spacings you can get 5 mil. The finer lines are possible, and one can go down to as low as 3 mil and 3 mil. And then we can get to even finer lines with etching. But anyway, the screen printing is limited to 5 and 5 for manufacturing purposes, and you can do a little better. In terms of the DBC and AMB, the line widths are 9 mil and the spacing 9 mil.
Excellent, thank you. What are the typical aspect ratio ranges of the hole diameter and height of the substrate for thick film, DBC, and AMB?
Sure. So if we take the aspect ratio as the diameter of the vias and holes divided by the substrate height, this ratio typically ranges between 0.3 to 1. Right, so that's the range, and the hole sizes range from 5 mil to 25 mil. So basically, if a substrate is really thick, let's say 40 mil, you would still go to 25 mil. However, having said that, it is possible to go to larger hole diameters, but they go beyond these ranges. So what has to be looked at depends on the substrate height. The actual range is between 5 mil and 25, and try to stay in the aspect ratio of 0.3 to 1.
Excellent, thank you. And I think we will close with this one. What are the typical operating temperature ranges for thick film, DBC, and AMB when using copper, silver, and gold metallization?
That's another good question, excellent question. So when one is only looking at the substrates, right, the metallized substrates, whether it is thick film, PCTF, direct bond copper, active metal braze, I mean, it can easily go up to 600 degrees C in terms of operation, but that's the limiting factor is not just the substrate, but the circuitry which is mounted on it. That means the soldering one is using, the solders one is using, sintering they might use, or brazing, wire bonds, semiconductors, and other components actually limit the frequency of temperature of operation. So typically, most of these applications will center around 250 degrees C, unless otherwise special metallization and other techniques are used.
Excellent, thank you. And to keep us on schedule, as I said, I think I will close this session here. So I'd like to thank Chandra again for the presentation and those great answers to the questions. And I'd also like to thank Remtec for sponsoring this workshop. The session has been recorded and will be available to watch at the end of the day. You'll find it on the EDI-CON online website. If any of your colleagues would find this informative, please let them know. And thanks everyone for joining this session and the next session entitled Revolutionizing Mobility from Connectivity to Insights with Innovative Automotive Technologies from Analog Devices will be starting at 10 a.m. Thank you.